Hey guys, and welcome to task 4.4, Features of Rational Functions. Today we're going to look at a bit more in depth at the graphs of rational functions. You're not going to be required to graph them yet, but what we're going to do is explore their features. By the end of this video and this task, I'm hoping that you are a master at finding the x-intercepts of a rational function, the vertical asymptotes of a rational function, and the y-intercept of your rational function. So we're going to look at some equations today and try to predict what those x-intercepts and vertical asymptotes are, and then verifying it with a graph. Now you have not seen very many rational functions, and if you can see this PDF of our notes today, they do look really bizarre. They have tons of variety, tons of different shapes, tons of different intercepts, asymptotes, all kinds of weird things going on. So let's just start by looking at some rational functions and seeing if we can develop a pattern. So here I have, let's go back to a simpler set. Here I have a set of rational functions and other functions. And I want to look at the equations, meaning these right here on the side, and look at the graph, the actual graphed equations, to see if we can see what they have in common. So I'm just going to turn them on, and I want you to see, what do these graphs all have in common? Again, what do those two graphs have in common? What do those three graphs have in common? How about that fourth one? What do we now have in common? What do these have in common? If you need to pause the video and stare at them for a bit, please do. What do the equations have in common? What do the graphs have in common? If you think you figured it out, fast forward about 10-15 seconds. I'm just going to keep turning them on and off, seeing if you recognize any patterns. What do they have in common? What do these two have in common? What do these two have in common? What do all of them have in common? Hopefully, you're noticing, at least in the graph, that they all pass through this point 3, 0. All of them. Every single one of these functions passes through the point 3, 0, or has an x-intercept of 3. Well, let's see how we can connect that to the equation. Our first equation right here does have x minus 3. X minus 3, that factor, leads us to an intercept of 3. The second equation, x minus 3 squared, we have that x minus 3 again. The third equation also has an x minus 3. The fourth equation also has an x minus 3, specifically in the numerator. And our last equation also has that x minus 3, again, specifically in the numerator. So I think we found our connection here. What do these graphs all have in common? They all have a factor of x minus 3. And what do they all have in common in their graphs? They all have an x-intercept at x minus 3. So that's the first thing we're going to jot down. How do we find the x-intercepts of a rational function? We find them by looking at the factors. But you'll notice that a lot of these functions have factors in both the numerator and the denominator. Our x-intercepts are going to come specifically from the numerator. So we're going to look at the numerator only for our x-intercepts, and we're going to set it equal to 0. So we set our numerator equal to 0. In this case, it would be x minus a equals 0, or x equals a, which means we have an intercept at a comma 0. At a comma 0. So that's going to get us our x-intercepts for each function. We can look at the numerator and know that all those factors in the numerator translate to x-intercepts. Let's compare that to a few more graphs to see if that holds true. So here I have another set of graphs. Let's just scan the equations. Do we see something they all have in common in the numerator? Scan those equations only. Is there something they all have in common in their numerator? Great time to pause the video and give yourself a little quiz on this. So what I notice is they all have an x plus 2. This first one, clearly x plus 2. The second one, I see that x plus 2 in the numerator. The third one, again, I see that x plus 2 in the numerator. This last one is a little bit trickier. I do see x squared minus 4, which factors to x plus 2, x minus 2. But they all do have an x plus 2 in the numerator. Well, what would that lead us to believe? Well, when we set that equal to 0, we should get negative 2. So every single one of these functions should have an x-intercept at negative 2. Let's test. And look at that, they do. They all cross through the x-axis. The red one, the green one, the orange one, the blue one, they all cross through the x-axis at negative 2. So if I'm trying to find my x-intercepts, I'm going to look at the numerator, and I'm going to look at those factors in the numerator to find my x-intercepts. But we've got some other things to explore. Let's explore our vertical asymptotes. Our vertical asymptotes are actually really similar to our x-intercepts. So let's look at a bunch of rational functions and let's see if we can develop a pattern. So my hint on this one is to look at these functions, see what they have in common. See what they have in common. So just look at the equation. So just kind of scan through this list and look at the equations. Y equals x divided by x minus 2. Y equals negative x plus 1 divided by 10 x minus 2. Y equals negative 1 over 12 times x minus 2. Y equals 1 over x minus 2. Y equals 1 over x minus 2, x plus 3. Y equals x squared plus x minus 12, all divided by x squared minus 4. Do you guys see that they all have an x minus 2 in the denominator? All of them, including that last one, which would factor out to x plus 2, x minus 2. They all have an x minus 2 in the denominator. Now, if that were in the numerator, we would expect an x-intercept at 2. But it's in the denominator, so let's see what happens. Let's turn them all on. Just going to graph them all right on top of each other. And I want you to kind of decide what's happening at 2. Well, what's happening at x equals 2? What's happening right there is that they're all kind of repelling away from 2. They're all kind of magnetically drawn away from 2. None of them are even touching the x-axis at 2. And in fact, they all kind of have this positive and negative end behavior, just going directly up to positive infinity and directly down to negative infinity at 2. Well, what am I describing here? This thing that is almost magnetically drawing lines in but not ever touching it. These lines just kind of flying off to positive and negative infinity but never actually touching 2. We're describing an asymptote. I know it's hard to see because they're all kind of right on top of each other, but they all have asymptotes at 2. There's one of them you can see really clearly has that asymptote at 2. There's another one you can see really clearly has that asymptote at 2. And another one, it looks slightly different, but as we zoom out, we see, yeah, that has an asymptote, or it kind of repels away, it breaks at x equals 2. Every single one is going to have that same kind of asymptote shape at x equals 2. So how do we find vertical asymptotes? We do the same thing we did for x-intercepts, but this time we're looking at the denominator. So we're looking at our denominator. And we are setting the denominator equal to 0. Looking for those factors. So in this case, x minus b would set equal to 0, and we would get x equals b, and that is our vertical asymptote. That's the goal. We want these equations x equals, x equals, x equals. So that's going to be how we find our vertical asymptotes. Now, before we try some practice problems, let's remind ourselves, how do we find a y-intercept? You guys have been finding y-intercepts since before Math 1, but that's always something we kind of forget about. For the y-intercept, it really is asking, where is our graph when x equals 0? So what we're going to do is we're going to plug in 0 for x. And we're going to plug it in for all of the x's. So my example for this one would be f of 0. 0 minus a over 0 minus b would just be a over b. So it would be the point 0, comma a, b. Don't be afraid to get some fractions for the y-intercept. You will definitely have some fractions because let's think back to what we're doing. We're doing rational functions or fraction functions. So let's just do the first example together. I'm going to go step by step, referencing these notes we took above. Let's start with the x-intercept. I know we find the x-intercepts from the numerator, so I'm going to focus in on this right here. And I'm going to say, well, it could have been x minus 3 equal to 0, or x plus 1 equal to 0. Again, we are setting that numerator equal to 0 and finding all the factors. So add 3 to both sides, x equals 3. 3 comma 0 is one of our intercepts. Subtract 1 from both sides, x equals negative 1. Negative 1 comma 0 is our other intercept. Let's check the graph. Let's see if we got that right. Well, positive 3, there it is. Negative 1, there it is. We found it. Let's go for the y-intercept next. We're going to be plugging 0 into the function. So I'm actually going to do f of 0 equals 0 minus 3, 0 plus 1, 0 minus 1, 0 minus 4. 0 minus 3 is just negative 3 times 1 times, divided by negative 1 times negative 4. So we get negative 3 over 4. So this is the point 0 comma negative 3/4. Let's see if that matches up to the graph. Yeah, that matches. It's just a little bit shy of negative 1. It's exactly what we wanted. So for our x-intercepts, we factored and solved in the numerator. For our y-intercept, we did the reverse. Instead of setting it equal to 0, we plugged in 0. Now let's go to the vertical asymptotes. Vertical asymptotes, I'm looking at the denominator, setting it equal to 0. So I'm going to explore just these two factors right here. X minus 1 equals 0. And x minus 4 equals 0, setting them individually equal to 0. Add 1 to both sides, x equals 1 is our first asymptote. Add 4 to both sides, x equals 4 is our second asymptote. Let's check out the graph and let's see if that actually fits. So here we have x equals 1, and yeah, I see this kind of vertical line that our graph is broken around, our graph kind of like repels away from. And right here at 4, I see the same exact thing. It's a break in our graph. That's exactly what we want to see with our vertical asymptotes. So let's finish up this example by doing our domain. Our domain is connected to our vertical asymptotes. If we think about every single number that we could plug into this function, well, this end goes off to negative infinity. But it stops right here at the first asymptote. That first asymptote is at 1. It picks up again immediately after 1. It picks up immediately again after 1. But it stops again at that second asymptote, 4. And then it picks up again after that asymptote, and it does head out to positive infinity. I like to think of this almost as a number line. My number line goes from negative infinity to positive infinity, but my vertical asymptotes right here at 1 and 4 tell me that the graph is open here at 1 and open here at 4, but it's filled in everywhere else. Everywhere else works except for 1 and 4. So that kind of matches how I think about my domain. Negative infinity up to 1, in between 1 and 4, and then 4 to infinity. Okay, go ahead and try some of these practice problems on your own. There will be a second video just running through solutions on some of these, not all of them. Have fun, guys.